Chemistry time. We're going to talk about ionic bonds. Ionic bonds.
You smiled the wrong way.
What's that even mean? Okay, ionic bonds. We're talking about ionic bonds. So ionic bonds are formed when what happens? When something's attracted. A bond is an attraction between atoms.
Isn't there two different ways? Or is that...
Well, there are two different kinds of, well, there's lots of different kinds of chemical bonds, but we're going to talk about two at first.
A positive ion and a negative ion are attracted to each other?
Good. I'm going to put exactly that. Formed when a positive ion, we have a name for that. I'm going to put positive ion, but you should know that that's also called
a cation.
Okay. Formed when a positive ion and negative ion are attracted to each other. And what makes them attract?
Well, they're opposites.
Yep. That's true. It's not quite the answer I was looking for. You're right. That is exactly true. But I'm looking for the name of the force that attracts them.
Oh, would it be like one of the four?
Yeah, it's one of the four fundamental forces of the universe. What is it? Yeah, you're right. What did you say, Hayes?
Electromagnetic.
The electromagnetic force holds them together because positive attracts negative and vice versa, right? Opposites attract. Oops, I forgot to switch this to picture-in-picture. There we go. Now you can see it better. Anyway, so the electromagnetic force holds them together.
And then isn't there another way?
There is another type of bonding called covalent bonding. There's two more basic kinds. There's covalent bonding, which we'll talk about in a few lessons, and then there's metallic bonding, which is different. We will talk about that in this chapter, but it's a different thing. Sorry, go ahead.
When I was reading, I thought there was another way they could do it is if like one of the nucleuses are attracted to each other.
The nuclei do attract the electrons of the other one.
Yes,
but,
that.
Yeah, and that's how covalent bonds form. Period.
That's the covalent.
But no, it's true for ionic bonds too. It's just that the attraction between the ions themselves is stronger than the attraction from nucleus to electrons.
Okay.
But yeah, that's right. So how do they become ions? We talked about this last time. How do they become ions?
If they have different numbers.
When they gain or lose electrons. If they have a different number of protons from electrons.
Yeah.
So and we talked about this several years ago. But just like the example I always give for this is just like your parents really wish you didn't live with them anymore because you're teenagers. They can't just say, get out of my house and never come back, right? They have to have somewhere else for you to go. And it's the same way with electrons. The electrons can't just leave to empty space, right? An atom can't just get rid of electrons because it feels like it. So if we have, for instance, I'm talking about like metal. Let's draw a simple metal here, lithium. Here's the lithium nucleus. How many electrons does lithium have altogether? 3. It has 3 electrons. It has 2 in the 1s orbital, and it has how many in the 2s orbital? 1. How many valence electrons does lithium have? 1. It has 1 valence electron. Lithium has 1 valence electron. That's supposed to be part of a circle. So lithium has 1 valence electron. How many does it wish it had?
8.
Or
2.
2, right? It could also get rid of this one and have a full valence shell with 2.
That would be easier than gaining.
Exactly. The easier way would be for it to lose the 1. But just like I just said, it can't just say, see you later, electron, right? It's part of it. Just like you're part of your family. They need to have somewhere for you to go, right? They have to say,
that's so sweet.
they have to say, you're going to go off to college or you're going to go off to Arby's, but either way, you have to, it has to have somewhere to go. So where can it go? Where does the electron go?
An electron that needs to gain one.
You mean another atom that needs to gain one.
Atom.
Such as, give me an example.
Fluorine.
Fluorine. Fluorine would be, thank you for choosing one easier to draw. Let's draw fluorine because it's easier. So it has 1s2, right? What comes next? 2s2. And then 2p5. 2p5 in this case. So we should stop. Normally I would draw the p's as a different shape because they have the dumbbell shape, but in order to make it easier, I'm just drawing Bohr models. So 1, 2, 3, 4, 5. So how many valence electrons does it have altogether?
5.
It has 5 valence electrons. It has 7 electrons altogether, but 5 valence electrons, right? Oh, I'm sorry. No, that's wrong. It has 7 valence electrons. You're right.
Yeah.
1, 2, 3, 4, 5, 6, 7. Yeah. And so the lithium is like, hey, my buddy fluorine wants an electron, and I've got an extra one, so away it goes. Maybe a better example would be like, you still want your Game Boy Advance, but you don't really use it anymore, so you're going to give it to a loving home. Or a puppy dog. That's probably more relatable because you guys were dead back when the Game Boy Advance came out, or you weren't alive. But your puppy dog, that's a very good example because people are always like, free to a good home, right? No one's going to be like, hey, you want some puppy for dinner? Come get this dog, right? It was your dog for a while. You wanted to, same thing with lithium, right? Other than the difference
like
is...
if you have like a dessert and you're too full and you don't want to throw it away,
That's even better.
and you are like, hey sister, would you like the rest of this cake? And your sister likes
I like
cake.
to imagine that it's just some lady and you're like, hey sister, because that's the way you talk.
No,
no,
it's not.
Right. So, yeah, but the difference being that what? The difference being that what? What's the difference in all of those examples with this? These things don't feel or think, right? They're just atoms. All this happens because of fundamental forces of the universe, not because they have any kind of will of their own. So anyway, yeah, go
That
ahead.
has 6 before, and then it gains a 6?
No, it has 7, and then it's going to gain this one as an 8.
Oh, okay.
So, our new, when they're ions, what's lithium going to look like as an ion?
2.
So it has 9 left.
Yeah, 2, but now it has a
No,
what kind
it
of
has
charge?
8. So fluorine is in
It has
the
a
7
negative.
column.
Right, it had
So it
7.
has a positive charge.
Fluorine had 7, it's gaining 1 more, so now it will have 8. Electrons, yes. It had 7 valence electrons.
How many just electrons?
Okay, so lithium now has only 2 electrons, which it's happy with, right? It's more stable with 2 electrons, but it also has what kind of charge now?
It now has a positive.
Now it has a positive charge. Whereas the fluorine now has a negative charge with how many electrons? 1, 2, 3, 4, 5, 6, 7, 8 with a negative charge.
Opposite as you would
Yeah,
think.
right, because electrons have a negative charge, when it gains an electron, it has a negative charge, right?
Mhm.
So, what's holding them together now? Whoop.
Is it
Your
electromagnetic force?
Electromagnetic force. The electromagnetic force holding together. And this holding together by the electromagnetic force is called a what? A or an? What's this thing here called? Okay, it's some kind of bond. What kind of bond is this?
Covalent.
No,
Not covalent.
that's right.
No.
Ionic.
Ionic.
The one that's not covalent is called ionic. This is an ionic bond formed between 2 ions. That's why it's called an ionic bond.
Forms between.
So, just as kind of a side note, well, let's have 2 side notes. What's the new electron configuration of this, the lithium ion?
1s2.
End of story, right? 1s2. Same as what? Same as the ground state electron configuration of helium, right? So it's like a noble gas. What's the electron configuration of fluoride? Oops, the fluoride ion, I mean.
1s2. 2s2. And then 2p6.
Yep. Which is the same as the ground state electron configuration of neon. They are most stable when they're configured like noble gases. The other side note is, just even from the drawing you can tell this, what happened to the size of the lithium atom compared to the size of the lithium ion? It got smaller, right? It lost a whole orbital. What happened to the size, this is a little bit trickier, what do you think happened to the size of the fluorine atom compared to the size of the fluoride ion? You have more electrons, but actually it got smaller because now there's more electromagnetic attraction between the nucleus and the electron, so it pulls them closer. There are more electrons, and so it's more attracted to the nucleus. So really, in both cases, it gets smaller. That's, like I said, it's a side note. But let's now, I'm going to pause it real quick. I think that's...
You know that's contagious.
Okay, so we're still talking about ionic bonds. I just erased it because of stupidity. So here are some properties. Here are some properties of ionic compounds. So, we should say, an ionic compound is what's formed when those 2 things have bonded. Here are some properties.
Properties of what?
Of ionically bonded substances. So we had in our last example the lithium ion, and what did we call the other ion? It's not called fluorine anymore. It's called what?
Fluoride.
Fluoride. So we named that thing. First of all, it's this. It's LiF, right? And the name of that is lithium fluoride. Right? We name it lithium because that's the name of the cation, and then fluoride because that's the name of the anion. That's what that thing was called. So lithium fluoride is an ionically bonded substance. Lithium fluoride is an ionically bonded substance. And so we can expect it to have these properties. Ionically bonded substances have high melting points. Very high melting points. Have you ever seen melted sugar? What is melted sugar called? You know? What?
Molasses.
Not quite. Molasses is like
I
a
think of like the sugar
byproduct.
stuff, like the sugar wax.
Melted sugar, not dissolved sugar, but melted sugar is called caramel. That's what caramel is melted sugar. Have you ever seen melted salt? No, salt basically, you can't melt salt, right? Salt has a melting point of something like 1700 degrees Celsius. It's ridiculously high. These ionically bonded substances have really high melting points, but they have extremely high, I'm going to put extremely high boiling points. Remind me real quick, what is a melting point and what is a boiling point? The melting point is where it does what?
Melts.
Yes, turns to a
Liquid.
liquid, whereas the boiling point is where a liquid turns to a gas. Right? There's a slightly more complicated definition for that, but effectively that's true. They have high melting points and extremely high boiling points. They're also always crystalline.
Always what?
Crystalline. If you're in earth science, you know that we sometimes call these crystals, depending on some other factors, we might call these crystals what? What kind of things have a crystal structure?
Igneous?
Maybe some rocks, but more specific, or not just rocks, but crystalline structure is a property of
Minerals.
minerals. Good.
Ah.
Yeah, minerals. So some minerals are ionically bonded substances, but they have a crystalline structure. All ionically bonded substances have a crystalline structure, and all minerals have a crystalline structure, but not all ionically bonded substances are minerals and vice versa. But all ionically bonded substances have a crystalline structure, what we sometimes call a crystal lattice. And this just means that it has a repeating pattern of ions. So in our last example, we had lithium and we had fluorine. I'm going to use red for fluoride ion. Should be a little bit bigger. And then we're just going to have a repeating pattern of that over and over and over again. It forms a three-dimensional structure. And the lithium fluoride is cubic, which means that this little pattern here will continue as long as it can in all three dimensions, making a cube. Pretend that I kept drawing those little dots. But the cube would be made of lithium ions and fluoride ions. This is called a crystal lattice. Oops, wrong marker, wrong way. Because it has a crystal lattice and because of the way these are shaped, I'm going to try to make it a little bit more robust. If we hit lithium fluoride or a piece of salt, maybe we had a great big piece of salt and we hit it with a hammer, what would it do? Break? It wouldn't bend? Which would it do you think? What if we, like, think about a crystal. If you hit a crystal with a hammer, will it break or bend? Break, yeah. And that's because this is what we call brittle. They are brittle. And that's because, if you think about it, right now, just these two, this fluoride ion and this lithium ion, are they attracted to each other or repelling each other? Attracted, because they both have a positive one. Well, this has a negative charge and this has a positive charge, so they're attracted to each other. But if we hit it with a hammer and we move everything one atom over, now what's going to be touching? They're repelling, because the fluoride will touch the fluoride. So basically, when we shift the crystal lattice even a little bit, the whole thing breaks down. That causes them to be brittle. So brittle. They also form electrolytes in solution. Electrolyte. You know about electrolytes. What's got electrolytes in it?
Gatorade.
Gatorade's got them electrolytes, right? An electrolyte just means that the solution in water conducts electricity. Why is this important for your body? What part of your body needs you to be able to conduct electricity? Or what part of your body uses electricity to function? Those things need it because they get electrical signals from what?
ATP.
Your brain. Your nerves carry electrical signals, and they need electrolytes to carry that electrical signal. So sometimes, rarely nowadays, but sometimes if you don't have enough electrolytes in your blood, your muscles can't receive nervous signals anymore, which makes you have convulsions and stuff. So normally you've got plenty of electrolytes, but the electrolytes are important in your body. And these electrolytes form because This one's got what kind of charge? I said this was fluoride. Negative. And this one's got what kind of charge? Lithium. Positive. And then if we draw a little water molecule, you remember water molecule? What's water's formula? H2O. So here's our O, and here are two little baby H's. And remember, this is a polar, we'll talk about this again later, but we did talk about it in physical science. This is a polar molecule, meaning that the electrons like to hang out with the oxygen more, so this gets a partial negative charge, and they like to hang out with the hydrogens less, so it gets a partial positive charge. Basically, the fluoride, because it has a negative charge, is attracted to this end, and the lithium, because it has a positive charge, is attracted to that end, and the water rips this apart. That's why salt dissolves in water. You put a little chunk of salt in there, and the water rips it apart. The positive, in the case of salt, the positive sodium is attracted to the negative end of the water, and the negative chlorine is attracted to the positive end of the water, which is what dissolution is. When salt dissolves, that's what's happening. And that forms an electrolyte. That new solution conducts electricity. Questions?
No.
The end.